4.3, number 29, we're asked to, it says use the derivative of the function to find the points in which it has a local max, local min, or inflection points. Alright, so here's what we're given. The derivative is x minus 1 squared times x minus 2. So the first thing I'm going to do is I'm going to graph the derivative, and we have to think back to our Algebra 2 days. We've got a polynomial. It's got zeros or x-intercepts at 1 and at 2. So that's what makes, if you set it equal to 0, 1 and 2 will make 0. It's a third degree polynomial. It's a cubic because we have squared here and then to the first, so combined it's a cubic. Leading coefficient is positive. There's a 1 out front, so the general shape is going to look like that. Third degree cubic looks like that. We also have a double root at x equals 1 because it's x minus 1, the quantity squared. So it's going to bounce off the x-axis at 1, and it's going to go through at 2. So we need to fit this shape going through here and bouncing off here. So we'll say there's my graph of my derivative. So that's y prime. Alright, so based on that, looking at first at x equals 2, to the left of 2, the derivative is negative because it's below the x-axis. To the right of 2, the derivative is positive. So the derivative goes from negative to positive. The original function y, if you have a negative derivative, is going to decrease, and afterwards, since the derivative is now positive, it's going to increase. So if it's, the original is going to go decrease and then increase at x equals 2. That means we have a local minimum at x equals 2. So local minimum at x equals 2, we know that much. At x equals 1, the original derivative is negative, then it's 0, and then it's negative again. So a decrease, the original function is decreasing, and then it's flat, and then it decreases again. So you can imagine it's decreasing, flat, and then decreasing again. So it looks like we have an inflection point at 1 at x equals 1. That's the shape of the general, or the original graph. So we know that the slope of the derivative represents the second derivative of y. So we know right here that the slope of y prime is 0, therefore y double prime is 0 at this point. Now does it change concavity? The second derivative right here, remember the second derivative represents the derivative of y prime, so the derivative of this function, if you think of it as a little slope right there, we have a positive slope. So right here the second derivative is positive. To the right side of it, we can see that the derivative of y prime, or the second derivative, is negative. So it goes from positive second derivative to negative second derivative, so there's clearly an inflection point at x equals 0. So x equals 1, I'm sorry, at x equals 1. Okay, in order for it to have a max, the first derivative must be 0 or undefined. We only have the first derivative 0 at 1 and 2. Those are the only possibilities. There's not going to be a maximum. But it looks like there is another inflection point, because right here we have a second derivative of 0, because the derivative of y prime is 0 right there. Okay, and on the left side it's a negative second derivative, on the right side it's a positive second derivative, because that's the slope of y prime. So it does change concavity right here. So we need to figure out, we can't really find that with the graph, so you have to find the second derivative. I'm going to use a product rule. So x minus 1 squared times the derivative of x minus 2, which is 1, plus x minus 2 times the derivative of x minus 1 squared is 2x minus 1. So y double prime equals x minus 1 squared plus 2x minus 2 x minus 1. Now I see that I have an x minus 1 factor in each of them. Rather than distributing all of them all out, I'm going to factor out an x minus 1 from each term, and I'd be left with x minus 1 plus 2 x minus 2. Just a little bit easier using that algebraic technique. So we are still trying to find where the second derivative is 0. That's our goal. We should get 1 is one of our answers because we just concluded that at 1 our second derivative is 0, and you can see that's the factor right there. So x minus 1, x plus 2x is 3x, minus 1 minus 4 is minus 5. You can set those both equal to 0. We get x equals 1 as one inflection point, which we already knew. So 3x equals 5. So x equals 5/3. And looking at the graph here, my little sketch, 5/3, 1 2/3, that looks like 1 2/3 to me. So we do have an inflection point also at x equals 5/3. Again, we don't know what the y value is because we need the original equation for that. We could find the antiderivative here, but we'd have plus c, and we don't know what c is without an initial value. So this is what we know.